Okay, I'll make a video here on chapter 13. There's some confusing, tricky stuff in here. So it'd be good to go over all this stuff. Okay, so it's on gravity and how it interacts with things like us and how moon and planets interact and all that kind of stuff. So we know that Isaac Newton wrote down his universal law of gravitation, F equals G m1 m2 divided by the distance between m1 and m2 squared. Oftentimes in this chapter, M1 and M2 will be like planets or the sun or something. Or maybe one will be a planet, one will be the sun, or one will be a planet, one will be a person, or something on the planet. And let's do the case where one of the mass of one is of the planet, and one is the mass of something on the planet, like the Earth. In that case, if F is equal to Gm, where maybe M is U, so here you are. If you're someone with longer hair. Okay, so there's you, and then big M is the mass of the planet. So you're standing on a big planet, and then the distance would be the radius of the planet. So we'll call that the radius of the planet. So this has a big mass of mass M, so it'd be the radius of the planet squared. So the force of gravity on you would be big G, which you all have memorized, times your mass, times the mass of the planet, divided by the radius, the distance to the center of the planet squared. Okay, now we also know that the force on you is what we've been calling gravity, and that's equal to mg. Your force on you to the Earth is mg, right? We've been saying that forever. The gravity is mg if you're on the Earth. So if we set those two things equal, which I just did, which is legitimate, that the force of gravity is this, which is this, the masses cancel, and we can find little g. So little g, which is called like the gravitational field, which we know on the surface of the Earth is like 9.8 meters per second squared, for any planet is big G times the mass divided by the radius of the planet squared. So if you're on the surface of the planet, it's big G times the mass divided by the radius of the planet squared. If you're not on the surface, it's how far you are from the center. Okay, so from the center of the planet. So if here's our planet, and here's the radius, and you're standing a radius above it. So here you are. What is G there? So in this case, G would be big G times M times 2 times the radius. So 2r from the center. So always a distance from the center. You are now 2 times the radiuses from the center. So squared. Square both of those. And so that is Gm over square that. 2 squared is 4r squared, which is 1/4 the gravity what it was. So if it's 10 at the surface, it's only 2.5 out here. It's only 1/4 what it was because it drops off as distance squared. If you go 3 out, it's 1/9. If you go, right, so here it's 1/4. If you go 3 distances from the center, it's 1/9. If you go 4 distances from the center, it's 1/16, etc., etc. That's the way it works. Now, if you go inside the Earth, then gravity gets smaller. And if you get the center, there is no gravity because you're getting pulled equally in all directions, which does not mean you get pulled apart. That's the weird thing. Instead, gravity cancels and you just float. So you think like, oh, you're getting stretched apart. But you don't get stretched apart. It could be a huge, gigantic thing, and it'd just be zero because gravity cancels. So in the very center, you would float. So as you go deeper and deeper into the Earth, gravity gets less and less and less. It goes from 10, nice and linearly, down to 0, and you can float. So if you could make a big tunnel in the center of the Earth, it'd be really fun because you could have a gravity-free, you could float around the center. Problem is it's hot down there, and the tunnel would melt, and yeah, lots of problems. Okay, so this would be our formula here for the gravitational field. R is the distance from the center of a round object that you're on. Okay, so that's one big thing to know from this chapter. Like I said on the Zoom thing, we're not going to go over the ocean tide stuff very much. We do that in astronomy. It's good stuff. I suggest you read it. But black holes and stuff, again, we go over in astronomy. Black holes are cool. That's where, well, we'll talk about that, the escape velocity and stuff. We'll do that kind of more next chapter because it makes more sense. So, yeah. But anyway, you should read it all. Good stuff. Let's do some more examples of problems because that's tricky stuff. And you're supposed to do these on your own. I think some of you did a pretty good job, but they're definitely tricky. So, like number 39 says the mass of Earth is about 80 times out of the moon. Its radius is about 3.7 times out of the moon. Calculate the acceleration due to gravity in the moon. So that's all the information we have. Okay, so like number 39 here. So again, we can just use ratios. If the mass is 80 times more, we know G on the Earth, and we can say it's 10, or you could use 9.8 if you want. Oh, let's use 9.8 with that. Is 9.8, and G on the Earth is, it goes as big G m divided by the radius of the Earth squared. Okay, so let's say if Earth, so the mass is 80 times out of the moon. The moon is 1/80th, so whatever G is on Earth, the moon is going to be 1/80th. So on the moon, G is going to be 1/80th as big because it's 80 times smaller, and it goes by mass. So you'd think, oh, divide by 80. However, it's also 3.7 times smaller, and that's on the bottom. So if you divide by 3.7, it's 3.7 times smaller, not 3.7 times bigger. So the smaller it is, the greater the gravity, and it goes by squared. So G on the moon is 1/80th times 3.7 squared times G on the Earth, and G on the Earth is 9.8. So we can just multiply that out, and we should get what G on the moon is. And you should get, it's about 1/6 or so. 3.7 squared, okay, I'll just do it. 3.7 squared is less, okay, 3.7 x squared divided by 80 is 0.17, which is about 1/6, so about 0.17 meters, times 9.8. Yeah, times 9.8. So 0.17 times 9.8, which is about 1.67, yeah, let's say 1.68 meters per second squared. Okay, so again, you just kind of reason it. 80 times less mass, gravity's smaller. 3.7 times smaller, gravity's bigger. The smaller the planet, the bigger the gravity, because the radius increases. If we took the Earth, we talked about this in the Zoom meeting, we squished it down and made it smaller, and you're standing on the surface, there's going to be a lot more gravity. If you squish it down to half the size, gravity will be 4 times bigger. A 1/2 squared in the bottom is like multiplying by 4. 1/2 is 1/4. Dividing by 1/4 is like multiplying by 4. So you make the Earth big, giant, took the Earth, squish it down to half the size, and you stood on it, you would weigh 4 times as much, which is be heavy, right? It'd be hard to stand up. So the smaller the planet, the greater the gravity, the less mass, the weaker the gravity. Okay, so these are all just ratios. You don't even have to know the mass of the moon or anything. Okay, so that's that one. A lot of these are ratios like that, right? Like number 42. What would the weight of a 1 kilogram mass be on the surface of Mars? And they tell us the mass of Mars is 0.11 that of Earth, and its radius is 0.53 that of Earth. So right away on Mars, we know, okay, mass is 0.11, so it's going to be 0.11 times weaker. G is going to be 0.11 times weaker, less mass. It's 0.53. Radius is 0.53. So they're giving us as a fraction here, so that's going to make it 0.53 times squared on the bottom. Dividing by a 0.53 squared makes it bigger, so that works, right? It's going to be bigger because it's smaller. So it's a smaller planet, so this is the same, if it's 0.11 times the mass of the Earth but the same size of the Earth, it'd be weak gravity. But oh no, it's a smaller planet too. So here we divide by 0.53. And again, we know we better get a bigger number. If we divide by a small number, we divide by 0.53, we get a big number, which works out. And it's squared. So that's that times 9.8. That's what G on Mars would be. So again, a lot of this is just kind of logic because it helps reason out the ratios here. So we know that the point of lens needs to make it smaller. We know this has to make it bigger. So we divide by it, that makes it bigger. So I go 0.11 divided by 0.53 divided by 0.53, and I get 0.39, so I go times 9.8, so about 3.84 maybe. 3.84 meters per second squared is G on Mars. They say what would the weight of a 1 kilogram mass be? So weight is mg, so 1 times that right? So it's just that. So it'd be 3.84 newtons. They made the math easy, gave us 1 kilogram. Okay, so again, these are all just kind of using ratios, knowing how this formula works. All right, so get number 43. I think these are fun. It's kind of cool stuff. 43, many people mistakenly believe the astronauts on the Earth are above gravity. They're only 200 kilometers above the Earth's surface. Okay, it's not very much different. So we're at the radius. Okay, so yeah, so they give us the numbers here, and so all we got to do here is calculate g. So g is equal to big G times the mass of the Earth divided by the radius squared. Big G, you all have memorized, is 6.67. Why did I put a times symbol there? 6.67 times 10 to the minus 11th. I'm going to make sure everything's in meters and everything. Mass, they told us, is 6.0. You can just write 6, you don't need the 0.0, but it tells us that even to that decimal place it's a 0. Times 10 to the 24th kilograms. And then you divide by the radius, how far you are from the distances. Okay, here's the tricky part. 200 kilometers. The radius of the Earth is 6380 kilometers. So 6380 kilometers plus 200 kilometers. That would make that one get bigger there. So that would be 6580 kilometers. But we have to put meters in our formula. So we multiply that by 10 to the third to change the kilometers to meters, because that's 1,000. So it's 6580000 meters, and that's squared in the bottom. Now we could write that as 6.580 times 10 to the 6th meters. Again, you have to put meters here. That works. So 6.580 times 10 to the 6 meters, and then you square it. So many people forget to do that. I've graded so many tests, people forget to square it. Okay, now we just do the math and figure out what G is at the space shuttle, only 200 kilometers above the Earth, which again is very far, because the radius of the Earth is 6380 kilometers, right? 200 compared to that, those numbers are practically the same. So we know we're going to get a number pretty close to 9.8. Now, the way I suggest you do this, or you could do it, is do the scientific notation separately. So you go 6.67 times 6 divided by 6.580. Okay, so I'm going to do that. And that's about 6, right? Because 6.67, 6.58 practically cancel. And then we have a 6 left. So we know our answer should be around 6. A little bit less, a little bit bigger than 6, because this one on the top is a little bit bigger. But let's figure it out. 6.67 times 6 divided by 6.580. I get 6.082. So, which, yeah, a little bit bigger than 6. So 6.082 times 10 to what? Well, here we have 11. So we have a negative 11 on the top. We add those. You add the powers of 10. Negative 11 plus 24. 24 minus 11 is 13, right? So you have a 10 to the 13th in the bottom. Oh, sorry. This is squared. Okay, don't do what I just did. I didn't divide by 6.580 twice. So it's divided by this twice, 6.580. I forgot to do it the first time. I knew something was wrong. Okay, the square in the bottom. Okay, don't just write the squared, actually square it. 10 to the 6th squared. Okay, so 6.580 squared, I got divided by that again. 10 to the 6th squared is 10 to the 12th. So we've got 10 to the 12th on the bottom. 10 to the 13th divided by 10 to the 12th, you go 13 minus 12. That's just 10 to the 1, which is just 10. So our answer is just 10. Multiply our answer by 10. So we take this, divide by another 6.580, because I only did it once. So divided by 6.580. And I get that, multiply it by 10. And I get that it's 9.24 meters per second squared. So 200 kilometers above the Earth's surface, about 160 miles. It's weaker. Gravity is weaker. It's not 9.8, it's 9.24. Not a whole lot weaker. If you were standing there, you would probably notice it. It'd be kind of fun to try to figure that out, but you know, not a huge difference. Okay, last one I want to go over here is the tidal force. Okay, so number 45 is kind of cool problem. It says find the tidal force of a planet on you to see if it can have any effect. You can choose your own planet. What an opportunity. Okay, I'm going to choose Venus. Okay, so let's, because Venus is the closest planet, and it's bigger than Mars and bigger than Mercury. Now, Jupiter is way bigger, but it's also 5 times further away. Okay, so I know that Venus is, I know its distance from the Earth. Its distance from the Earth is 0.3 AUs. I know that from astronomy. It's 0.7 AUs from the Sun. We're 1 AU from the Sun. And an AU is 93 million miles, or 150 million kilometers. So it's 0.3 times 150 million kilometers, which is, just write that out, kilometers, which is, wait, I can do that in my head. That's 0.3 times 150 is, 3 times 150 is 450, so 45 million kilometers. So 45 million kilometers. And I want meters, so I'm going to make that meters. There, add 3 more zeros for meters, which let's change that to scientific notation. 4.5 times 10 to the 9 to the 10th meters. Okay, that's the distance that Venus is away. And I just looked this up online, planetary fact sheet, that I know the mass of Venus is 0.33 times that of the Earth. Oh, wait, no, sorry, that's not right. This table has it as times 10 to the 24th. So the mass of Venus, this is the distance, that's mass is 0.33 times 10 to the 24th kilograms. That's how this chart gives it. Okay, I think that's all we need to know. Now, earlier, they tell you a formula on page 197 here. They give a formula which they just work out for the tidal force. So we had to figure out what those numbers are. So the tidal force is 4 GMR divided by D to the 3rd power. Okay, so what do these numbers mean? And basically, D here is this, how far is the distance. Okay, here's the idea. Let's say you are a sphere. Here you are. And you have a radius D. And way far away here is Venus. Here's Venus. And Venus is a distance r away from you. Okay, a distance r away from you. Wait, I did that wrong. Is it the other way around? It's got to be the other way. Yeah, it's the other way around. It's okay. The way these numbers work. R is your radius, how big you are from the center to the outside, and this is D. Okay, you got to get these letters right. This is D, the distance between your center and some planet's center. Now here's what the tidal force means. Venus is going to pull harder on this side of you than it will on this side of you, because this side of you is closer. Now you're not a sphere, but whatever, we can pretend you're a sphere. So that's called a tidal force, that you're getting pulled harder on one side than the other. And that's what makes tides on the Earth and makes the moon actually stretch a little bit. If this is the Earth, this is the moon, we kind of stretch the moon apart because we pull harder on this side of the moon and that side of the moon. So this side of the moon is just kind of sitting there and we're kind of yanking this side away from that side. So I call that a tidal force because it's what makes the tides. So it's kind of cool. Okay. So we just got to plug the numbers in here. So it's getting them right. Now let's say that you're, make the math easy. Let's say you're 2 meters, about 6 meters tall. About 6 meters tall. About 6 feet tall. Okay, 2 meters is easy math. Therefore R is 1 meter because that's easy math, right? I'm about 6 feet tall, so that works. So let's say R is about 1 meter. Most people are roughly good enough, right? Because we're not spheres anyway. So, okay, so R is 1. And we just figured out that D was this, 4.5 times 10 to the 10th. So we can plug all these numbers in. 4 times 6.67 times 10 to the minus 11th times the mass of, and this is the mass of Venus. Yeah, your mass doesn't matter because all it's doing is how hard is it pulling on one side versus the other side. And we know the mass of Venus, I wrote it down there, is 0.33 times 10 to the 24th kilograms. And the distance we weigh, we figured that out, was 4.5 times 10 to the 10th. And we got to cube it and not forget to cube it. First, not forget to write it and not forget to do it. Okay, so let's plug in all these numbers. First, let's do the numbers, then we'll do the scientific notation. So 4 times 6.67 times 0.33 divided by this thing 3 times, divided by 4.5 3 times. So let me do that. 4 times 6.67 times 0.33 divided by 4.5 divided by 4.5 divided by 4.5. I get that is 0.0966, good enough, times 10 to some power. To get the power, we have a negative 11 and a 24 on the top, like we did before. That gives us 13, so 10 to the 13 on the top. On the bottom, we have a 10 to the 10 3 times. So that's 10 to the 30th. 10 to the 10 times 10 to the 10, 10, 10. We add them together 3 times. That's 10 to the 30th. So 10 to the 30th in the bottom. 13 minus 30 is 17, negative 17. So 10 to the minus 17. So 10 to the minus 17. And we made sure these are all kilograms and meters and everything. Yeah, the radius is 1, right? The radius there was 1. We said the radius is also 4 GM. Yep, did everything right. So that's how many newtons it is. 10 to the minus 17th newtons, right? That's 17 zeros here. That's a tiny force. Venus is not going to stretch you apart. Now, if Venus was a black hole that was really close, that had a huge mass, a much, 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 much bigger mass, it'd have to be about, well, 10 to the 17th times, or 10 to the 18th, or 10 to the 19th times bigger, right? If it was 10 to the 40th or something here, 60, no, even bigger than that, 10 to the 45th, then we start getting a real force. Then that makes this like a 10 squared, 100 or something, and then it starts getting to be a real force. So tidal force is going to be big near black holes or something, but you got to be, either have a huge mass or be a lot closer. We can't have such a big number in the bottom. And the closer one is what matters most. It's to the 3rd power. A lot closer makes a big difference. Okay, that's how you do 45. Okay, that was chapter 13. I'm going to make another video on chapter 14, and hopefully all this stuff makes sense.